All right, we are going to begin by covering section 1.1 in the textbook titled Systems of Linear Equations. This is the section of chapter 1 that kind of gets us into the basic ideas of what this class is going to be about. So let's get started. So what I want to do first is actually start by defining a few things that might be helpful as we move through these first couple of sections. So most people in this class understand what a linear equation is, but we want to define it in a slightly different way. So as you can see, a linear equation in the variables x1, x2 through xn is an equation that can be written in the form a1x1 plus a2x2 plus dot 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 plus an xn equals b. And in this situation, we are going to let b and the coefficients a1 through an be any real or complex number. For the most part in this course, we will be dealing with real numbers, but there is a section later on in this course where you have to be comfortable doing this stuff as complex numbers, and we'll talk more about that when the time sits. Now, in this example, we have, in this class, a system of linear equations. So what if we have multiple linear equations all put together? Some books also call this a linear system. You'll hear me call it both throughout all the videos in this class. But we can think of a linear system as being a collection of one or more linear equations involving the same variables, let's say x1 through xn. So kind of a brief little example that you might be familiar with is this one you see on your screen. So as you can see, I've got three equations, 1, 2, 3, and each of those equations has three variables that are all added together, and then they are equal to some constant that we are calling b from the beginning of this slide. Now, what you might recall from a previous algebra class is that in order to solve for the exact answer, typically we want the number of equations to match the number of unknowns. Well, that is what they teach in most lower level algebra classes. We will see throughout this course that that may not always be the case. Our goal is to find a solution of these linear systems in this course and then interpret what that means. So a solution of a linear system is a list of numbers that in this chapter we will use S as our solution. Each of these numbers makes each equation a true statement when the values of S1 through Sn are substituted for the x1 through xn respectively. So if you were to take the numbers that you found as your solution and substitute them back into the originals, say this equation back up here, it should make each statement true. If any of them are false, it is not a solution to that system. Now, we may find some that have more than one solution. So the set of all possible solutions is called the solution set of a linear system. So we'll be looking at sets where they can have infinitely many answers in this case. Another thing you'll hear me say occasionally is what happens if two linear systems are considered equivalent? That will only be the case if they have the exact same solution. So kind of a brief little example here for y'all to see is I've made two systems up here. Each of these has two equations with two unknowns. Now, before we get into the linear algebra way of doing this, a quick little review of what you might recall from a basic algebra class is that when you have two systems, one of the methods you learned is that if two of the variables are already opposites of each other, then you can add the two equations straight down and solve directly. For example, x1 plus 2x1 would be 3x1. The x2's would cancel when you add them together, and then this is equal to 1 plus 2 is 3. Dividing both sides by 3 would give you x sub 1 is equal to 1. And then if you substitute this back into either equation, I'll just pick the first one here, I can definitely see that 1 plus something needs to equal 1. So thus, x2 is equal to 0. Now, if you look over at this second system that I've made up, it does not match the first one because while one of the equations is the same, the second equation is completely different. But if you were to solve this the same way, the difference being is that I would actually subtract these two equations because I can see that 3x1 minus x1 is 2x1. If you subtract the x2's, they go to 0, and then 3 minus 1 is 2. Once again, dividing by 2, we can see that x1 is going to be 1, and if I plug this back into the original, let's say the second one this time, I know that 1 plus 0 is equal to 1, so thus x2 is 0, and so both of these systems have the same solution set of the point 1, 0. So what we can now say is that since these two systems are not the same thing, since they yield the exact same solution, we actually call them equivalent. And that idea is going to be fundamental in us setting up the idea to solve larger systems by using matrix algebra in this course. All right, so let's kind of go back one more time to some stuff you've probably learned in a previous algebra class that's going to help us in this course. So what we simply just did is that when you find the solution set of a system of two linear equations with two variables, this is pretty easy as you saw, because all you are essentially doing, or what I essentially just did, is I was finding the intersection point of two lines. All right. So giving you a second example, if you had x1 minus 2x2 is -1, and negative x1 plus 3x2 is 3, as you can see below, if you were to graph those two lines in the same plane, all you are trying to do is figure out at what point do they intersect each other. So visually from this picture, you can see that they intersect exactly one time at the point 3, 2. So 3, 2 would be our solution to this particular problem without having to actually do any work. As you can imagine, that's a little bit more difficult to do when you start adding more variables and thus move into higher dimensions in this course. But for right now, this simply kind of shows you the first thing, that in the systems that we're going to solve in this class, this is an example of having exactly one solution, which is what's going to happen a lot. If it only intersects once, you have one solution, and we call this a consistent solution of the system of equations. Now, there are two other situations that can also happen. As you can see on the left, and I modified the lines just a little bit so that you could see the difference. If you use these two lines over here on the left, you will see that they actually end up being parallel to each other, which you might recall from 2 dimensions means they have the exact same slope. But for our argument is that if two lines are parallel to each other, as you can see here, they are never going to intersect each other. And when two lines don't intersect each other, they're never going to form a point of which a solution would be. So thus, you will have no solution, which we will call an inconsistent solution as well. The third situation that can happen is, what if you have two lines that are, well, let's say equivalent everywhere? So as you can see on this third example, when I took these two lines and I graphed them, what ended up happening is that L1 ended up equaling L2 everywhere. So when you draw the lines, it looks like you just have one line going across the point. So since they intersect everywhere because they are the same line, you might recall that this means from algebra that you have infinitely many solutions, which for us still means that it is a consistent solution. So the two words you've seen on the last two slides is that whether it be a unique solution, which means one answer, so exactly one, or whether it means infinitely many solutions, that means you have a consistent system. The only time you will have an inconsistent system is when you do not have an intersection point of the lines that you are working with. So now the question becomes, how do we take this idea from maybe a basic algebra class and now put it into more of a matrix algebra form? So the first thing is we're going to define a couple different things about the original matrix. The essential information of a linear system can be recorded compactly in a rectangular array that we call a matrix. So let's assume for a second that this is the system that we want to work. X1 minus 2x2 plus x3 is 0. 2x2 minus 8x3 equals 8. And 5x1 minus 5x3 is 10. There are two different kinds of matrices that we can pull from this information. The first one, as you can see, is called the coefficient matrix. So a coefficient matrix means you are going to take the coefficients of the variables on the left-hand side of your equations, and you're going to put those numbers into a matrix form. So if you look at the first equation, there's a 1 in front of the x1, a -2 in front of the x2, and a 1 in front of the x3. That is where those three numbers are coming in the first row of our coefficient matrix. All right. In the second row, you'll notice that there is no x1 term. So you'll then have to put a default 0 in. So when you don't see a certain variable in a certain equation, we understand that as being a 0 coefficient. And so you would continue that for everything on the left-hand side of each equation, and thus you have your coefficient matrix. The second kind of matrix we're going to look at is called an augmented matrix. An augmented matrix is essentially just a coefficient matrix with an extra column added on to the end. Now, this extra column that you'll get means you have to incorporate the coefficients that are on the right-hand side of the equation. We called this the variable b a little bit earlier in our definitions. So the 0, the 8, and the 10 becomes your last column of the augmented matrix. Now you'll see next to each of these matrices that I have the dimensions written out. So if you're not as comfortable doing that, let's review this. When you read dimensions of a matrix, you always read it as row by columns. So this would be a 3 by 3 matrix. There are 3 rows, there are 3 columns. Versus the second one, there are still 3 rows, but now there are 4 columns across the top. So we would read that augmented matrix in this example as a 3 by 4 matrix. Once you set up these matrices, which we're going to focus more on the augmented matrix in a minute, how do you go about solving a matrix in this form? So as you can see on your screen, the basic strategy to solving a linear system is to replace one system with an equivalent system, i.e. one with the same solution set that is easier to solve. So roughly speaking, you want to use the x1 term in the first equation of a system to eliminate the x1 terms in every other equation. Then use the x2 term in the second equation to eliminate every other x2 term, and continue this until you're done. The thing is, there's only 3 ways that you're allowed to do this. So these are the only 3 steps we will look at over the next few days. They're called replacement, interchange, and scaling. In a replacement, what you will try to do is you will replace one row by the sum of itself and a multiple of another row. For interchange, that's a nice one there. All you do is you can interchange 2 rows. And for part 3, you will multiply all entries in a row by a non-zero constant, which is called the scaling technique. The key on number 3 is it has to be a non-zero constant. I always have a student once in a while who will try to multiply everything in a row by 0. That's not going to be allowed, and it's not helpful for that matter at all. So these are the 3 strategies, which we call the elementary row operations, that we are going to use to solve these matrices. So what I want to do now is I want to work some examples of using this idea to find solutions of linear systems. Now, as I go through these problems, some of y'all are going to be thinking, well, I could do it this way like I learned back in, let's say, a college algebra class, and that's fine. Just know that there's a method to this idea that will help us going forward. So in example number 1, I want to find the solution to the system x1 plus 5x2 equals 7, and -2x1 minus 7x2 is -5. So what I will do first is I want to set up the augmented matrix of this system. So I will begin by pulling the coefficients off of the x's that you see. So in the first row, there is a 1x1 and a 5x2. So I'll use 1, 5. In the second row, it's negative 2x1 and negative 7x2. So negative 2, negative 7 is my constants. And then in my extra column that makes it augmented, I will use the 7 and negative 5 that are on the right-hand side of each equation. So now my goal is to reduce this so that I can take, as you saw earlier, we want to take the x1 in the first row and we want to use that to eliminate everything below it. So what I would like to do is I'm going to try to eliminate the negative 2. So 9 times out of 10, you're going to be using that replacement strategy in order to do this. So here's kind of how that works. I want to take row 2, which is the number, once again, we're focusing on the negative 2 right here. If I were to take that negative 2 and I were to add 2 row 1s to it. Now, once again, even though I'm saying row 2 and row 1 for right now, I'm focused on the 2 numbers in the first column. So I'm wanting to take the negative 2, and if I add 2 times the 1 that I have circled, we should all know that negative 2 plus 2 is 0. So what I have just done is I have formed and changed that bottom left number into a 0. The problem is that whatever you do to change the first number in the second row, you have to do the same operations all the way through. So if I move over to the negative 7 now, all right, negative 7 fall in the same order. Negative 7 plus 2 times the number above it. So negative 7 plus 2 times 5 is going to give you 3. And then one more time, if you move to negative 5, negative 5 plus 2 times 7, which would be 14, gives you 9. So I changed the entire row 2 in the same manner that made sure the negative 2 went to 0, and then everything else fell as it is. All right. Now that we've eliminated everything below this 1, now we want to move to the x2 column in the second equation. So that's where the 3 is at. All right. And we need that to be the number 1 and then eliminate everything above it. Well, since that is the number 3, the first thing I want to do is make that 3 a 1. So we'll do that. So I'm going to take row 2, and we can multiply everything in the second row by any constant other than 0. What I notice is that everything in row 2 is divisible by 3, so why don't we multiply everything by a third? When I do that, the second row, we will get 0, 1, 3. So I multiplied everything by a third in the second row. And now you can see that 3 that we wanted to be a 1 is now exactly that. And now you want to use that 1 to help you to get rid of the 5 that's above it. So now I want to manipulate or replace row 1. So focusing on the 5 and the 1, here's how you'll do that. I will take row 1, and which is the 5, and I want to subtract 5 times row 2. So in my mind, I'm taking the 5 and I'm subtracting 5 times 1, and I know that 5 times 5 is going to be 0. So while I'm not changing row 2, I have already immediately changed the middle column of row 1 to be a 0. But remember, you have to change everything else in row 1 in the same regard. So if I go back to the first point, you would take 1 minus 5 times 0, which is still going to be 1. And then if I take 7 and subtract 5 times 3, so 7 minus 15 would be negative 8. Once you have done this for every row possible, what you have just done is you have just found an equation that represents the solution to this problem. So now you have to remember, what do each of these rows actually tell you? Well, if you read, based on how you labeled the augmented matrix at the beginning, that first row tells us that x1 must equal -8, and the second row tells us that x2 must be 3. And thus, the solution to our system is the point -8, 3. And so what you could do if you would like is that if you plug these two numbers back into both original equations, you should get two true statements. So that shows you kind of the intro to how we're going to solve matrices in this course by doing this row replacement strategy. Let's do another example. This one's going to have a few more variables in it, but we can work it the exact same way. So example 2, what is the solution to x1 minus 3x2 equals 5? Negative x1 plus x2 plus 5x3 is 2, and x2 plus x3 is 0. Similar to the last example, the first thing you want to do is set up an augmented matrix. So I will start my matrix. And from the first equation, your coefficients of the variables is going to be 1, -3. There is no x3, so we'll put a 0 there. And then we'll repeat this for everything else. You should get -1, 1, 5 for the second equation, and then 0, 1, 1 because there is no x1 there. Then I'll use the three coefficients on the right to finish off, 5, 2, 0, and this forms my augmented matrix. So going back, you want to circle the x1 position in the first row, and you want to get rid of everything that's below it. Well, the good thing is that there's already a 0 down there in row 3, so the only thing you're trying to get rid of here is that -1 in row 2. So focusing on just that column, if I were to take row 2, which is the -1, and I were to add the row 1 that I have circled, that would make it go to 0. Now remember, we're not messing with anything else just yet. Row 1 and row 3 are remaining the same. But remember, you fixed row 2, you have to do the same thing throughout. So if I move to each successive number in row 2, you're adding the number that's in row 1 right above it. So this would be 1 plus -3, which is -2. Then 5 plus 0 is 5. And 2 plus 5 is 7. So we have gotten rid of everything that's below the x1 position in the first column. Next thing you want to do is technically you want to move to the x2 position of the second row, which is -2. But as we know, that would be a lot nicer if it was the number 1. My first thought is to multiply everything by a -1/2, but as you can see, that's not going to make the numbers next to them very nice. Instead, the other technique we talked about is you are allowed to interchange any two rows at any point. So it looks like if I were to take row 2 and interchange it with row 3, it would move this 1 into a better position that might make our math a little bit easier. So let's see what happens here. 1, -3, 0, 5. So I'm flip-flopping or interchanging row 2 and row 3. So you'll have 0, 1, 1, 0, and 0, -2, 5, 7. Now it looks a little bit nicer because now we have that 1 and we want to get rid of everything that else is in that column. So we have two things to do here. We have to get rid of the -3 in row 1, and we have to get rid of the -2 in row 3. So we got to do two steps at once here. For the -3 that's above it, we're going to take row 1 and we're going to add 3 row 2s because -3 plus 3 times 1 would be 0. Likewise, we're going to take row 3 with the -2 and we're going to add 2 times row 2, which will be -2 plus 2, which is 0. So when we do that, we did not mess with row 2 here. In row 1, if I take every element and add 3 of the number below it, you'll get 1 plus 0 is 1, negative 3 plus 3 is 0, 0 plus 3 is 3, and 5 plus 0 is 5. For row 3, you're going to take each element and add 2 of the number above it. So 0 plus 0 is 0, negative 2 plus 2 is 0, 5 plus 2 is 7, and 7 plus 0 is 7. We're going to keep moving on right along. We're done with column 2. Now we move on to this 7 right here, which will be the next number we have to deal with. Now notice you can't interchange the number right above it this time because that would mess up the row you just fixed. But instead, this time, back to what we talked about in the last problem, with row 3, each of those numbers is divisible by 7. So why don't we just multiply everything in row 3 by 1/7? So that would be 1, 0, 3, 5, 0, 1, 1, 0, 0, 0, 1, 1. Now my third number is a 1 like we wanted to, and we're going to eliminate the numbers that are right above it. So to do that, we got to fix row 1 and we got to fix row 2. To get rid of that 3, I have to take row 1 and subtract 3 row 3s, because 3 minus 3 would be 0. And for row 2, all you have to do is just subtract row 3. So 1 minus 1 would be 0. So we're not messing with row 3 this time. So leave it alone. For row 1, if I take all those elements and subtract 3 of the numbers in row 3 that match up, you'll get a 1, a 0, a 0, and then 5 minus 3 is 2. For every number in row 2, you're going to subtract the number that's right below it, which would be 0, 1, 0, negative 1. And now that you've gotten your 3 points and everything above and below them is a 0, you can now write out what your answer is. So the first row of our matrix says that x1 must be 2. Row 2 says that x2 must be negative 1. And row 3 says that x3 must be 1. So when you write your solution here, the point 2, negative 1, 1 is the solution set for this system of linear equations. So a few more steps there than the last one, but that is your basic idea. This is how you can take any set of linear systems and you can reduce it down and find what the answer to it is. All right. So example number 3 is worded a little bit differently because for the first time, we're not asking for the solution. Sometimes in this course, we just want to know, is it actually possible to work a certain problem out? So here's kind of my example to show you this. Determine if the following system is consistent. Which remember, all consistent means is, does a solution exist? So we've got x2 minus 4x3 is 8. 2x1 minus 3x2 plus 2x3 is 1. And then 4x1 minus 8x2 plus 12x3 is 1. So what you'll do is you will set up your augmented matrix again. So we're going to have, let's see. If we write out all the numbers in row 1, that would be 0, 1, negative 4, then 2, negative 3, 2, and then 4, negative 8, 12, and adding the numbers on the end to make it augmented is 8, 1, 1. So now in this case, for the first time, we actually have a 0 in the upper left-hand corner, which we do not want. All right, we always want the number 1 there if we can. Now your instinct may be to interchange row 1 and row 2 here, but I actually wouldn't do that. If you interchange row 1 and row 2, you're just going to put a 2 up there, which that row's not really doesn't simplify as nice. What I notice is that in row 3, those numbers are a little bit better and they are divisible by 4, or at least majority of them are. The 1 on the end is not very nice, but in the end, that's not going to make a big of a deal. Since more of these numbers are divisible by 4, what I'm going to do is two things at once. I'm going to interchange row 1 and row 3, and I'm also going to take the new row 1 and multiply everything by a fourth. So let's make sure we're okay with this. First thing is row 2 is not changing. Okay, so there's row 2. The row 1, I'm moving down to row 3. So 0, 1, negative 4, 8. Now this row 3 that I'm moving up to row 1, we're going to move it up there and multiply everything by a fourth. So 4 times a fourth is 1. Negative 8 times a fourth is negative 2. And then 3, and then 1/4, which is an ugly number, but we'll deal with it here in just a few minutes. So you got your 1 there. Now you want to get rid of that 2 that's right below it. So to get rid of that 2, I'm going to take row 2 and subtract 2 row 1s. So row 1 is not changing. If I take every number in row 2 and subtract 2 times the number right above it, 2 minus 2 is 0. That will be negative 3 plus 4, which is 1. 2 minus 6, which is negative 4. And then 1 minus, and then 2 times a fourth is a half. So 1 minus a half is a half. And then we're also leaving row 3 alone for right now. So far, so good. You dealt with column 1. In row 2, your x2 position is already a 1, which is what we want. So you're just trying to get rid of the number that's above and below it. So that's two things. We got to change row 1, and we got to change row 3 accordingly. In row 1, to get rid of the negative 2 that's right above it, I would take row 1 and add 2 row 2s. And for row 3, to get rid of that 1 right below it, that would just be row 3 minus row 2. So the middle row you are leaving alone. For the top row, row 1, you're going to add 2 times the number right below it, which would be 1. Negative 2 plus 2 is 0. 3 minus 8 is going to be negative 5. And then 1/4 plus 1 would be 5/4. For row 3, you're just going to subtract the number that's right above it, which would be 0, 0, 0. And then 8 minus a half is going to be 15/2. As you can see, we now have our first problem that we've seen in this class. While it was nice to get the 1 here and the 1 here, unfortunately, there's not a way to get a 1 in that position because you don't want to interchange any of the rows because that's going to mess up the ones you already fixed. At this point, we're kind of stuck. And what we have to think about is, what does this last row now say? Since we can't go any further, the last row, if you think about what each column represents, this is saying that 0 equals 15/2. Because since there is no x1, x2, and x3 values, we don't have any variables, which means they all go to 0. It has to equal the constant 15/2. And this, as we all know, is a false statement. Now, as you know from earlier, or maybe you know from a previous class, a false statement like this typically means no solution, but make sure you're answering the question of the problem. It didn't ask what the solution was. It asked, is it consistent, yes or no? And since there's not a solution that will solve this, your answer is no. This system is not consistent because you cannot find a solution. There's no need to keep going. Once you're done, you're done. All right. And then to wrap up this first section of chapter 1, a little bit of a critical thinking question. This question says, determine the value or values of H such that the given system is a consistent linear system. So we just want to figure out what can we let H be to guarantee this will always give you a solution. That could be one number. There could be more than one number. We won't know until we're done. My suggestion for the fourth time in a row is when you have to solve a system, write out your augmented matrix. So in this case, our augmented matrix would be 1H, 2, -8, and then the two numbers on the end are -5 and 6. Starting in the next video, I won't do these all separately. I'll just write all the numbers down in each row, which you've probably gotten used to by now, but for this first video, I wanted to break each part down. So when you go to row reduce this or do your replacement strategy, you've already got your 1 and you're trying to get rid of the 2 that's right below it. So I would take row 2 and I would subtract 2 row 1s. So that doesn't mess with row 1. But if I take every number in row 2 and subtract 2 times the number above it, you should get 0. You'll get -8 minus 2h, because we don't know what h is yet. And then you'll have 6 plus 10, which is 16. So now, piggybacking off the problem that we just did, this is as far as you can go. Since we don't know what h is, we can't row reduce this any further or any strategies. We're never going to make this a 1 unless we know what h is. So what we're going to do instead is think about what has to be true for this to be consistent. And so remember, consistent means it could be exactly one answer, or it could mean infinitely many answers. So first thing we know is that what's the problem? As long as it's consistent, we have a solution. So what we're trying to answer is, when is it inconsistent? Because that's the exclusions we want to keep. As we just saw in the previous example, I'll scroll back up for you. You do not want to have all zeros and then just a random number on the end. If that number was anything else that I have underlined other than a 0, so right here, if that was any other number, we could technically make it a 1 and then keep going. But if it's a 0, there's nothing we can do. So going back to the problem at hand here, if this right here is equal to 0, that's going to be bad. Because if that becomes a 0, there's no way we're going to solve this problem in any way possible. So if it's 0, that's inconsistent. So since the question is asking us when is it consistent, we want to take -8 minus 2h and figure out where it's not 0. Because if it's anything other than 0, we could solve this problem. If you were to work this out, move the 8 over, or -8 over. So -2h cannot equal +8. And if you divide both sides by -2, we have just found out that as long as h is not -4, you have a consistent linear system. Now, it's not asking us to stipulate when's it exactly 1 or when's it infinitely many. So don't overdo the work if you don't need to. It's just asking where is it consistent. So every h other than -4 is good to go. So that ends the video for section 1.1. In the next section, we will continue on these strategies, introduce a few new definitions, and talk more about how we solve matrix problems.